Good morning to one and all present here. I'm Sreshi Pal.
And I'm Abhishek. We are truly delighted to welcome you all to day 3 of the international conference rTIME 2025, the third chapter of advancement, wisdom, and knowledge sharing.
Today, as we carry forward this scholarly pursuit with two impactful and powering keynote sessions presented by distinguished experts joining us today.
Please join us in welcoming Professor Flammini from University of Florence, Italy, who is an eminent researcher in cyber physical systems and cybersecurity. He pursued his master's and PhD in computer engineering with honors from University of Naples Federico II, Italy. He is also a professor at Mälardalen University, Sweden, and he previously chaired the Cyber Physical Systems group at Linnaeus University, Sweden. With 15 years of industry experience at Hitachi Rail and IPZS, Italian State Mint and Polygraphic Institute, he has led major international projects in intelligent transportation and critical infrastructure protection. And he is a senior member of IEEE, which serves as a chair of the IEEE SMC Systems, Man and Cybernetics Technical Committee on Homeland Security. He has authored 100 plus publications and contributed widely as a speaker, editor, and committee member across global research forums.
Now, with utmost respect, we welcome Professor Flammini to grace the dais. Over to you, sir.
Good morning, ladies and gentlemen. I prefer to use a microphone, so I'm waiting for the technicians to bring me one. But maybe I can start in the meantime. And thank you for the invitation. Thank you for the nice presentation. I'm very glad to be here. And we'll talk. Okay. Okay, it's working. So maybe just needs to be closer to. Can you put it closer? Okay, so hopefully now it's okay. So we talk about the combination of technologies to move one step towards trustworthy autonomous systems, which is a very challenging goal. You see what is the situation nowadays. We have many systems that are automatic, but they are not autonomous. Moving from automatic to autonomous means a paradigm shift because you need to use AI, artificial intelligence, machine learning. So a completely different story. When you use AI and machine learning, you are using, for instance, artificial vision. And when you use these technologies, machine learning, artificial neural networks, convolutional neural networks, there are big challenges in terms of trustworthiness. So this is one of the main focuses of this talk. And how to address this is very complex multidiscipline problem. So we will focus on the roles of modeling and digital twins, and particularly for the safe perception. So in a complex systems, you have several subsystems. So perception is only one of the subsystems involved, and it is the one that perceives the environment. If you have an incorrect perception of the environment, then everything else in the system cannot work safely. Okay, this is not working properly. So we'll use the keyboard. Okay, so I like to take this from a very broad perspective at the beginning. So you have seen perhaps this image many, many times. This is the full picture of a smart city. And for what you do here, probably the most interesting part is smart manufacturing. So it's somehow borderline compared to the other smart city components. My main research interest is on smart transportation, but when I was at Melardine University, I also was a professor of computer science with a focus on cyber physical systems, and my main focus was on smart production, smart manufacturing, and all the technologies that are involved, including the industrial Internet of Things. And talking about Internet of Things, you see now this kind of statistics is quite old. I need to update it, but you can see the trend that is progressively increasing in terms of number of connected devices. So this is a phenomenon that everybody is witnessing, and it's the same in industry. So within smart factories, you have connected devices using these very heterogeneous protocols such as Wi-Fi, Bluetooth Low Energy, and many of these connection protocols are wireless, which poses a lot of challenges in terms of dependability, because if you use a wireless network, it means that it's an open network, so anybody can access your network in theory, so like the internet. So the protocols that you must use to secure the communications must be very robust. So that is one of the aspects, but there are many other aspects to consider. In general, what we need to develop is cyber physical systems that, as a matter of fact, are everywhere and are increasingly autonomous, so using machine learning. And we need to have them reliable, safe, and secure, especially in critical applications. Because in smart cities and smart factories, you have both critical and non-critical applications. For non-critical applications, you have, of course, less strict requirements. For critical applications, you need to apply international safety standards, which means that the certification process against those standards is can be very long and time-consuming and also resource-consuming. And it's a big challenge to manage the growing complexity, heterogeneity, because as I said, you're using diverse components connected using diverse protocols, and many, many uncertainties. So management of reliability, safety, and security means management of the uncertainty. What happens if this situation happens, how you manage this threat, and so on and so forth. So for this reason, quite some time ago, Jean-Claude Laprie, it's quite famous in my field research scientist, he invented the concept of resilience. As you can see from this slide, resilience is a combination of different factors. And it's not working. Is a combination of different factors. So you can see it's a combination of technologies, management of changes, and dependability. Dependability itself is a combination of three main concepts: attributes such as maintainability, reliability, safety, availability, integrity, and confidentiality. Threats can be faults, errors, and failures. And then means to achieve dependability, so fault prevention, fault tolerance, fault removal, and fault forecasting. Especially fault forecasting is the one that is model-based. So fault forecasting you do by developing models, and through models you can, for instance, estimate the reliability of the system, the safety of the system, etc. So as a very synthetic definition, we can say that resilience is the assurance of dependability in presence of changes. Because without the concept of resilience, if you only consider dependability, you're not considering the changes. But changes in the environment and in the system itself are very, very common nowadays. You have over-the-air software upgrades, changes in the environment. So the systems are not as they were 30 years ago. For instance, railways, I work a lot with railways. It's a very conservative domain. But things are changing very quickly, so you upgrade the software very quickly compared to what you did 50 years ago. You developed a system, and it was the same exact system and environment for 50 years. Now things are changing because customers are requesting more functionalities, more adaptation, more performance, and this reflects on more complexity to manage. So the basic concept, the most basic concept that we can consider to manage these big challenges is the concept of risk. Risk as a mathematical function can be very, very simple. So it's a combination of these three factors, which is probability of threats or frequency of threats, depending on the definition of risk that you want to use, either qualitative, quantitative, or a combination of the two. Then there is V, which is the vulnerability of the system against those threats. And then you have the third factor, it's the damage, D, or a measurement of the consequences of the threat. In some cases, you can measure in monetary loss. In some other cases, it's more qualitative because you have to deal with human lives. And then in order to quantify in terms of requirements, depends on the kind of risk. For instance, you have the mean time between failures, the total hazard rate. And for instance, this total hazard rate, it refers to safety critical systems that are used in when many people are involved, so typically transportation systems. So if the system fails, many people can be killed or injured. So this is the requirement. You have to be below this threshold of 10 powered -9 hazard per hour. Thank you. How you do that? You need to use models. So all engineers need to use models, especially if you want to demonstrate that your system is safe. You need to use model-based engineering, which is the most general approach. But then you have more special approaches such as model-driven engineering, model-driven design, and model-driven architecture. So this is more related to the software design. But in general, model-based engineering you can apply to both hardware and software, and co-design of hardware and software together. What I did in the past was to investigate the use of multi-formalism models in order to find a good trade-off between the modularity, compositionality of the models to adapt to the different kind of attributes or subsystems to be modeled. And as you can see, this is only a view, a theoretical view of how formalism can be combined. For instance, you have here a Petri net, which is very powerful. Petri nets with some characteristics have the same expressive power of the Turing machine, which means that you can model everything with Petri net. But sometimes they are difficult to use, difficult to maintain, and they suffer from the state space explosion problem if you want to use the analytical solvers. So they are not perfect for every kind of modeling. On the other side, fault trees, they are very simple, probabilistic combinatorial modeling of complex systems, so very effective, but they have very limited expressive power. So you cannot model, for instance, failure modes that are not only working or not working. You can have different failure modes because the systems are not very simple, like a light bulb that are working or not working. And with fault trees, you can only have two states in each event. So you cannot have multi-state events. So you can use, for instance, Bayesian networks. Bayesian networks is another very effective probabilistic modeling formalism that can allow you to model common mode of failures, multi-state events, and so on. So building a model like this is not easy. But when you can do this, you are able to demonstrate that your system is modeled properly and fulfills the requirements, then you are done. You can certify your system, and then you can get approval. So this is for any kind of critical systems. For manufacturing, for instance, you have cobots, collaborative robots. That is Industry 4.0 means connected machines, and also we are moving towards Industry 5, which is human-centered AI, basically, paradigm shift with humans involved in cognitive systems. So not necessarily autonomous systems, but semi-autonomous systems and decision support systems for the humans. And many of these systems are critical, so they need to, in order to be approved, because if they failed, people can be injured or die, you need to undergo these certification processes. In the end, you can get approval. The problem is with the new systems, new generation systems such as the cobots that I mentioned. Normally, in factories, you have these robot arms that are closed into cages. So that they are safe because they are closed into cages. When you remove the cage and you want workers to work together with robots, so they are named collaborative robots because they work together with humans, then the safety concern is very important. You need to address the fact that this robot arm can kill a person working with it. So this is why the situation is getting worse with the introduction of AI, machine learning, artificial vision, because if you want to have these new technologies, then it's even more difficult to model because systems are not easy to predict. Now, the classical example is autonomous cars, but autonomous systems can be everywhere, even in factories. And you have different levels of autonomy. So depending on the level of autonomy, there are some things that you can do today. For instance, level 2 is something that you can find in commercial vehicles nowadays. But if you want to move to level 3, 4, or 5, then it's starting to be very challenging. So we don't have basically full autonomous cars that are certified to be used in urban streets. Even level 3 is difficult to achieve. For instance, for Tesla, which is the most famous manufacturer for full self-driving cars, they didn't actually reach level 3, which means that there is a huge challenge. If these big companies like Tesla, Google, Google Waymo, they were not able to reach these levels of autonomy, then you can understand that it's very difficult to do that unless you control the environment, but that is a different story. What you have in addition to the normal threats that you have in all systems, even traditional systems, you have cybersecurity threats, well-known cybersecurity threats, and we are able to protect our systems against cybersecurity threats to some extent at least. But with the intelligent systems, you have the so-called adversarial attacks. So if you have an attacker that adds a noise which is invisible to human eye, that kind of noise can actually fool the system and make the system do a wrong classification. You see here in this classical example, instead of recognizing a panda, the system will recognize a gibbon, completely different animal to human eye. And the difference is not, we cannot perceive the difference adding that noise, but for the machine, that noise makes a huge difference in classification. So imagine if you do this for self-driving vehicles, you can change the shape of the signal that is perceived by the machine, and you can cause an accident. So this is intentional attack, but this kind of things can happen for any kind of different reasons. For instance, reflection of glares, reflection of solar light. So you need to take into account that what is simple for us as humans can be difficult for machines. So the problem is not obvious to address. So we need to address more in general what is called trustworthy artificial intelligence. And trustworthy artificial intelligence is a combination of robustness aspects, which is the most technical field. We as computer scientists, engineers, focus mostly on this aspect. But as I said, we need also to address the certification, regulation aspects. So it's the legal implications, and the ethical implications are also very important. So what we are doing nowadays in the research project, we are building cross-discipline teams with lawyers, with people that are experts of moral philosophy, all these aspects, because when you build an AI system, intelligent systems, you need to take into account not only the technical aspects, but also these other two aspects. And the intersection of the three pillars makes a system trustworthy. You see that, for instance, there are problems of interpretability, explainability, and transparency. Depending on the taxonomy, they can be given different definitions. But in general, they can be seen more from the technical perspective or legal perspective or ethical perspective. But you have this big problem that machine learning systems, for instance, they are not interpretable, they are not explainable, they are not transparent by design. So you have to work if you want to achieve explainability for these systems. And there is ongoing research. I would say there is a big research effort to make these systems explainable, because it's quite obvious that if we have this situation today in which you have an intelligent system that provides decision that you cannot understand, then you cannot trust. If you are able to make a system which is explainable, so when it suggests a decision and makes a classification, you know the process, you know how much you can trust it, you quantify the uncertainty, then you have the possibility to certify it. So now we go step by step, introduce some concepts that will be useful to address this big challenge. One concept that I found very useful to divide a very complex problem into sub-problems that are easier to solve is the concept of self-adaptive systems or autonomic computing. And they are based on this MAPE-K loop. MAPE-K means monitor, analyze, plan, and execute over a shared knowledge. So you see here in the middle you have the knowledge that is represented by the models. It can be the machine learning models, we will see Bayesian networks models, any model that represents your knowledge. And then you have the different steps. So you monitor what is happening in the managed systems using sensors, probes. You need to analyze, identify the solutions, select the optimal solution, and execute the solution. So this is why you need to go step by step to execute this. So this is a closed loop control, but it's more from the software engineering perspective. So you need to develop these modules and manage the knowledge independently. And now we introduce the concept of digital twins, although in this field, I'm quite sure that you know digital twins very well, but from the perspective of smart manufacturing, that is or predictive maintenance, that is the main field in which digital twins have been used in the past by NASA, General Electric, these big companies. They have started to address the runtime modeling, because a different way to talk about the digital twins is talking about runtime models, because these are models of the system that are very detailed models that are executed at the runtime. So they are basically fed by the data coming from the real systems. So without this Internet of Things, this concept of paradigm of cyber-physical systems, combining the physical systems and the digital part of the system, you cannot have digital twins. But when you have digital twins, you can do a lot of things that you could not do before, like, for instance, what-if analysis. So I want to make a change in the system, take a decision. I want to simulate it through the model before implementing it. You can do accelerated simulations and many other things, and you can predict failures before they happen, possibly using digital twins. So this is why digital twins are very important in also in safety critical applications. And now we can recap the connection between all these concepts. So this is a UML class diagram. I'm not sure if you know this formalism. It's a view of the unified modeling language. It's very useful to represent concepts, like in this case. You have a cyber-physical system in the middle, which is made by a cyber part. so edge, fog, and cloud computing, and the physical part, so basically sensors and actuators, or the hardware components. And then you have the Internet of Things or industrial Internet of Things if you are in industry. That is an enabler for cyber physical systems. Otherwise, you cannot collect data in real time. And on the other hand, as I said, the cyber physical systems are enablers for digital twin, because without cyber physical systems, you cannot have digital twins. And then on the top part, you have this machine learning focused latest developments. So you can have a cognitive digital twin when you reach a digital twin with AI and machine learning. So normally digital twin can have no AI and machine learning. It's simply a very detailed model of the real machine. And you can have autonomous cyber physical systems when you reach cyber physical systems with AI and machine learning. Now, the modeling of the system to be the digital twin is both a science and an art, because modeling needs to be adapted to the level of detail that you need for the system, and also the attributes that you want to measure. So if you want to measure reliability, it's different if you want to measure performance. So you cannot have a perfect model for everything. But let's assume that we can make a model for the things that we are interested to model and the attributes that we are interested to evaluate. The process is like this. First step, you build the reference digital twin model at design time. You instantiate a digital twin with the configuration data, and then you stop here for the design time. Then at runtime, so this dashed box here, you start to evaluate the digital twin model. In this case, we assume that you want to evaluate the system dependability, which can mean many, many things, because dependability is as we have seen, is reliability, maintainability, safety, security, and so on. But we have a target. Once we, for instance, safety, we need to evaluate if the target is achieved or not. If it is achieved, then we continue executing the system, and we continue monitoring the system if there is any fault or anomaly. Otherwise, if the dependability target is not achieved, then we need to compute reconfiguration options. So we need to change the configuration of the system in order to keep it safe, if it is possible to keep it safe. Otherwise, if it's not possible to keep it safe, what you do is to shut down the system, if it's possible to shut down the system, or to switch to fallback procedure, redundant system, human control. That very much depends on the backup options that you have. So this is done with the flowchart, classical flowchart. If we move initial state in which the system has no faults and anomalies, and then when you have faults, you move in degraded states. Can be minor degradation, or you can have a major degradation until you get to a compromised state in which you have critical faults. So this is another view of what can happen. And when you have the dependability target which is not achievable, again, you need to shut down or switch over to a backup system. So this is what you do with when operating in digital twins to monitor the dependability of your system. And this is another view. It's a more architectural, but more conceptual architectural view of how you can run these digital twins in practice. So let's start from the bottom. You have the physical assets, for instance, your smart factory, connected smart factory. So you have Internet of Things collecting the data and the status of your components. And this information is used to feed the digital twin. Again, inside the digital twin, you have the MapK loop. So it's a digital twin that basically is meant to monitor, analyze, plan, and execute actions on your managed system. So this is the managing system over the managed system, which is your physical system. One thing that I want to underline that here is not only physical part actually, but can also be software part. So it's both hardware and software that you are monitoring. It's not only the physical physical part of cyber physical systems. So I would say that here you have cyber physical systems that you are monitoring, or you can have, depending on the application. So when you are at this level, this level is known as the edge computing level, which is very close to the real components. When you move up, you want to move your data up using the internet. You have intermediate level, which is fog computing, which is maybe local data centers, which is not far from the real systems. At this can be at city level, urban level, regional level. And then you can move your data up to the cloud, which means you don't know where your data is. Can be anywhere. Sometimes it's a controlled cloud, so you know where is the data centers, but in some other cases, if you don't care about the security, it can be in any part of the world. What are the pros and cons? When you are closer to the machines, you have more confidentiality because your data is not shared over the internet. You have less latency, so quicker feedback loops, and more autonomy, because if you don't have connection to the internet, you still have the possibility of autonomy. When you move up to the cloud, you can manage more knowledge coming from all the instances of your systems that are installed, maybe more factories worldwide. Imagine a big company like ABB. They have their components, their robots installed all over the world, and they can collect data from all these components. And if there is an issue that has been detected in Japan, that information can be used to improve a system that is installed in India. So this is why you have maximum knowledge when you move up to the cloud. You have more power because you have very powerful computers and data centers, and you can also have more cost effectiveness because you concentrate everything in one single powerful big computer. Okay, so let's make a real-world example with a focus on perception. This is why we have chosen in the past this example of vehicle detection. Actually, can be anything, can be people detection in a smart factory, because you want to, as I said, for cobots, for instance, you want to use sensing capability of the cobot to detect humans in order to not to hurt humans working together with the robots. So there are many applications that you can think in which you use more sensors to detect a safety critical event. But we have used this data set in the past, this application in the past, because we had a data set available. So that is very important. It's not obvious that you will have a data set that you can use. In this case, for vehicle detection, we had a data set from US transportation, US government transportation agency, if I remember well, in which they did a study using more technologies, active infrared, microwave, video image processing. At that time, they were not using the word artificial vision, but it's basically using AI on video footage, acoustic, inductive loop. So you have many different sensors that you can use to detect the same event. So whether the vehicle is present or not. So it's a simple event, yes or no, but you can use different kind of sensors. So this is very important because you have redundancy and diversity. When you have redundancy and diversity, then you can achieve the levels of safety that you need. So what we did is to instantiate the same models that I have explained before. Now we will not go into the details again, but you can see the flowchart and the state chart as abstract representation. You can instantiate with this specific application of vehicle detection. You can instantiate for any specific application. And also we instantiated the MAPE-K loop, monitor, analyze, plan, and execute over shared knowledge. In this application, which is multi-sensor event perception, so you need to perceive. In autonomous robotics, more in general, the perception part, as I said, is very important. So you use more sensors to detect simple events. We will see also another application later. And here it's important to underline the fact that the knowledge is represented by dynamic Bayesian networks. So in this case, we found a very good trade-off between ease of use, expressive power, and solving efficiency, so also the efficiency of runtime operation using dynamic Bayesian networks. And dynamic Bayesian networks is a formalism that I love because they support explainable AI. They are explainable by design. So it's a formalism that was born in the past and was associated with AI. Nowadays, it's a niche use of Bayesian networks because most people are using neural networks, deep neural networks, which are more powerful. But if you want to achieve explainability or interpretability of the models, then Bayesian networks are much, much better because they are based on probabilistic approach and they are fully transparent and explainable. So using this approach, we were able to simulate failures in the sensing subsystem, starting from a configuration 4 out of 5. So 4 sensors must be working out of 5, and you compare the output of these sensors. So you have 5 sensors, this one, and then you want to agree on the decisions of the sensors when at least 4 of them agree. In this case, you have a probability of hazardous failures that is -7, around -7, which is not SIL4. Safety integrity level 4 you achieve only, you see this table, only if you have a probability of failures per hour that is lower than 10 power to -9. But SIL2 can also be used in many applications, so it's still a good safety integrity level. But what happens if you have some failures, then this SIL2, you need to reconfigure the system. So sometimes you can reconfigure to have SIL1. Safety integrity level 1 means that maybe you need to have a backup system because it's not the same level as the initial level. But you can also make a reconfiguration to make the system safe, for instance, using 4 out of 4, which means SIL3, so a higher level compared to the initial level. The fact is that when you have a 4 out of 4, you have a very high level of safety, but you have a very low level of availability because you need to find a trade-off between many different factors. So it's not only safety, but it's also availability. You can also have false positives. You want to minimize false positive. So the system detects that the vehicle is there when the vehicle is not there. It's safe because you stop, for instance, other vehicles. But if you have too many false positives, then the system will not operate with intended performance. Now, more recently, I've been working on this other project. So I moved from transportation systems like trains, big transportation systems, to very niche application that is autonomous wheelchairs. Even though the application is completely different, the issues are the same, and the perception system is, even in this case, made by diverse sensors that whose outputs must be combined in order to achieve the required level of safety of the system. More specifically, in this project, it's an EU-funded project in which there were different partners working together. My university, University of Applied Sciences and Arts of Southern Switzerland, and Dalle Institute for Artificial Intelligence. I'm still affiliated 50% with this institution. We have focused on the perception part. So how you put together all these sensor output in order to make the system safer. And you can see that it's not only the wheelchair, but it's the wheelchair supported by a drone. It's a visionary concept, because you can easily guess that in cities it's not easy to introduce drones operating together with the wheelchairs, but the regulation is evolving quickly from this perspective. And if you use very small drones, so micro drones or nano drones, they are more easily authorized to be used in urban environment. But this is not only about outdoor environment, it's also navigation in indoor environment. In those cases, the drone is used to map the environment. So it explores the indoor environment and maps the environment. But in the many different sub-problems that you need to address for this kind of system, as I said, we focus on the perception part. Safe perceptions means doing information fusion from redundant and diverse sources to make safe decisions. And the problem is that several sensors, they use deep learning, so convolutional neural networks, for instance, and cameras, for instance, they use those technologies. So in the end, you want to put together sensors that singularly you cannot trust, because you cannot trust a smart camera alone. But if you add more sensors, then you can do. And the important thing is that the drone can be used not only to provide more diversity in sensing of the environment in the perception subsystem, but it can also be used to provide diversity in terms of perspective. Because compared to the sensors that you have on the wheelchair, on the system itself, then this add-on, the drone can see the scene, the environment from a different perspective. So if you have occlusions, because the cameras that are installed on the wheelchairs cannot see the street clearly, then the drone you can put in a different side of the street, as we will see, and will provide an additional point of view. And this is exactly the scenario that we used as a reference scenario for testing. So you have the road crossing by the wheelchair. It's autonomous wheelchair, so the person is there but is not controlling the wheelchair, and needs to take a safe decision about crossing the road or not. You have a vehicle that is incoming, and you model the physical properties. So typical, it's distance, velocity, acceleration, etc. And then you have this object detection and tracking done both by the sensors on the wheelchair and the sensors on the drone, but you can see from different perspectives, different viewpoints. So this enriches redundancy and diversity. So the decision, as I said, is whether the autonomous wheelchair can cross the road or not. So the implementation that we did in the lab initially was based on these kind of robots. These are known as RoboMasters. They are used for research because they have open platform that you can configure relatively easily. And then in the laboratory environment, it's also very easy to build the ground truth. So the exact positions of the objects in the environment you get using the OptiTrack. OptiTrack is a tracker using these cameras. It's the same system that is used in movies to make special effects. And in this case, the precision of the detection of the objects on the scene is less than 1/100 of a millimeter. So it's very, very precise. And using that, you can build the ground truth. So the exact position of the elements in the scene, the RoboMasters that are simulating, for instance, the actual wheelchair, and the drones and the incoming obstacles. So here you can see a little bit better what we have done in the lab. So with artificial vision, you have the object detection and tracking, And then the ground truth, as I said, is achieved by the tracking system that is installed in the lab. So you can compare what is detected by the sensors on these RoboMasters with what is the exact position of the elements in the scene. At the beginning, we used very simple sensors. For instance, we didn't use LiDAR, but we used a range sensor unit that we installed on the RoboMaster. So we started with an indoor simple scenario in order to make a proof of concept that has been afterward extended to the real wheelchair. Oops. Maybe I'm moving too much. Okay, so again here the concept is based on the MAPE-K loop. So you see on this diagram on the right that on top you have the managing system, MAPE-K loop, monitor, analyze, plan, and execute over a shared knowledge. And then you have the manage the system, which is in this case a real autonomous robot, autonomous system. And as I said, we focus on the perception because you don't only have perception in autonomous systems. You have typically the other phases are planning and decisions, motion and vehicle control, system supervision. So these are aspects that we didn't manage. I mean, there were other partners and other colleagues that have managed. And okay, thank you. And yeah, and this is, for instance, a video of the simulation that we did in the lab. We defined a danger function, which is a mathematical function that I'm not showing here, but is a combination of physical elements and parameters like distance, speed, acceleration of the incoming object, of the object that can represent the danger. And so you build the danger function. The danger function is such that if it is below a certain threshold, then it's safe to cross. Okay. When the danger is above the threshold, then crossing is unsafe. It's very simple. You need to take a decision whether to cross or not, depending on the danger function. So you see in this case, the vehicle is incoming, and you have a view from the drone camera or wheelchair camera. And using YOLO, you have different performance depending on how you train the model. And so this means doing diversity, so using also different training data set for YOLO. But that is not enough yet, because in the real world, the situation, the environment is not perfect, but you can have environmental disturbances. You can have rain, fog, snow, whatever. And in those cases, the vision of, in general, sensors can be affected by these disturbances, especially artificial vision. You can easily guess that in these conditions, the cameras, they don't have the same performance. For instance, in low light, rain, heavy rain, fog, night conditions. Also, we tested with sun glares. I mean, many other different conditions. The performance changes. And you need to ensure that your system is safe in all conditions. It's not enough to say, okay, it's safe when it's good weather. No, in generally, you need at least to understand when it's unsafe. Okay, so it is also possible that it's not safe when there is a heavy rain, but you need to detect this condition and tell the user that, again, the system must be shut down, or another backup system must be used, or manual operation must be used. So for doing this, of course, we didn't put water in our lab, or fog maybe we could generate, but we used the software filters. So using software filters as these libraries that can put these artificial conditions on the scene is very effective. And this is a general problem that you have when you want to test autonomous systems, even self-driving cars. It's nearly impossible to make them operate in a real environment because you need a very long time. They should operate for millions of kilometers, and even in those cases you are not 100% sure that all these conditions have happened, because it depends on the geographical location, on the time of the year. So it's much more effective to simulate the critical conditions and test the system against those conditions. So you see here some footage of this is the initial simulation that we did in mainly in indoor environment, in which you have the testing on the wheelchair and the testing on the drone with the real user. This was important to collect initial data set, especially for the drone operating in indoor environment. Then we have won several awards for this application, because this is one application that has a very clear social impact. So from the perspective of the United Nations goals, having smarter cities, impact on the health, it has been recognized it has attracted a lot of attention by the media. And we have been working on more general results regardless of the specific applications. For instance, you see in this slide a general architecture of a digital twin from the perspective of the software implementation, because in the end you need to have a software architecture to implement the digital twin. And here you have the mapping between the MAPE-K loop and the layered software architecture. So for instance, the monitor is associated to this sensing module. The execution is associated to actuation module, and so on and so forth. And for instance, for the shared knowledge, you have this within the data layer, you have the persistence module to ensure the persistence of the knowledge. And in case you are interested, we have some papers that can share with you for further details. And another thing that is related to the usage of digital twins, but this is a quite different use compared to the one that I have shown before, but it's still very important to test autonomous systems, is using digital twins to represent the environment or the system itself. In this case, it's a different kind of digital twin, because it must be a very detailed model, for instance, of the environment, which allows you to test the system in virtual environments. Normally, what you can do is to have the real system, in this case is a train, in the real environment. This kind of testing, you can imagine, is very time consuming. It's safety critical, because if there is a problem, you have an accident happening on even if the train is empty. Of course, no passengers will be there, but still it can be a very serious accident. So this kind of testing you do only in the end, when you have finished all the other kind of testing. The opposite is having everything virtual, so virtual train in a virtual environment. And this is also something that has limitations. It's easy, compared to testing the real system in the real environment, but you have a gap of realism, so you cannot trust what is fully simulated. So you need to have some intermediate testing, which is, for instance, the virtual train in the real environment or the real train in the virtual environment. Both of these testing approaches are safe, because if an accident happens, it will be a virtual accident and not a real accident, because you will not have the two real systems working in combination. So one of the two components, either the system or the environment, will be simulated, will be virtual. So this is another way of using digital twins. In the past, this was better known as real-life simulators. For instance, you have heard GTA, I mean the video game environment with which you could build a virtual environment. They were called real-life simulators, but now they are tending to call them digital twins of the environment. So it's a matter of taxonomy. But regardless of the taxonomy, this is the situation that you can have. So for instance, we did in one project that we had about artificial intelligence for railways. We wanted to experiment with onboard obstacle detection for the autonomous trains. And with this approach, you can put, for instance, a virtual obstacle on a real track. So you can have a combination of a real system and the virtual system, because otherwise it would be dangerous to put real obstacles to test the obstacle detection function of the train. Okay, so we are close to 1 hour, 55 minutes according to my timer. And I just wanted to say a couple of things. As you can see from the template of this slide, I'm a member of the IEEE and involved in several initiatives within the IEEE. For instance, I'm in the IEEE System Man and Cybernetics Society. So in case you want to have more information about how to join the society or to build a local branch, student branch, local chapter, then I'm the person to contact, and we can discuss about that later or even at distance. So having said that, thank you for your kind attention. If you have any questions, I would be happy to answer.
I would say the presentation was really very informative. Like we all got to learn a lot in a very short time. And I have a question. I think the major problem when when you're crossing the road with the wheel, the delay which is there, like the communication delay, will that be a problem?
Yes, of course, this is about the real-time operation of the system more in general. And this is something that is common with all real-time systems. And autonomous systems used in safety-critical applications are real-time systems. So the communication delay is something that is you need to take into account. But this can be managed using safe approaches. I mean, if you can have these systems that are called watchdog timers, and you can check the timestamps. You can, for instance, understand if a message that you receive, for instance, from the drone, is not fresh enough to be considered in your analysis. So this is one approach that you can use in all systems. So you need to check the timestamps of the communication. So you have these safe protocols on top of unsafe means of communications, because if you use Wi-Fi, if you use Bluetooth, I mean, this by design, these are not safe by design. So you need to use a protocol over them to make them safe. So you need to use encryption, sequence numbers. You need to use timestamps, and with this, you can ensure that the information that you get is fresh. So you must consider it. Otherwise, you discard. And if you are not sure that everything is fresh and the computation has been in real time as required, you don't move. You stop. So in some applications, it's easier to do that. For instance, in trains, it's easier because in case of doubts, you activate the emergency stop, and no one will die because the train will reach a safe condition. For other kind of systems that I have not addressed here, can be self-driving cars, can be unmanned aerial vehicles. then it's not so easy to reach a safe state when you have a problem like this. But there is normally a fallback, a backup procedure in order to manage unsafe situations. But it's not so obvious that you can reach a safe state. Sometimes if there is a failure, maybe you cannot reach a safe state for an airplane, for instance. But for these systems, autonomous wheelchair, trains, then it's easy to, relatively easily to, easy to reach a safe state, because for the trains, I've worked many years. You have in the European railway traffic management system, for instance, you have a timer which is named TN contact. It's a few seconds. If the system is not controlled and receives fresh messages from the check site within this timer, within a few seconds, then the train starts to brake. So everything is controlled. It's not that you can trust messages that maybe have been lost in the network and they are old, so they refer to a condition that is not the real condition. Yeah. So this is how it is managed.
Thank you, sir.
Good morning, sir. My name is Suman Saurav, and welcome to our institute, sir. My question is that, sir, how did that AI reach to a specific decision of what is going to happen? What is the final decision we have to take? And second question is that, how is that system prone to any attacks or attacks to any data and data leakage? Thank you, sir.
Okay. So very good question. Okay, so first thing is about the new paradigm. I would say someone says that with AI you are not going to you don't have to test only the output but the outcome of the decision, which is not the same thing. For instance, if you test the output, it can be a safe output, but then the outcome, which is the more long-term implication of the decision, can be unsafe. So the typical example is the again Tesla that brakes suddenly in a tunnel. So this is very common for self-driving cars, that they brake suddenly in situations in which they don't have to brake. And okay, apparently the output is safe, because if you brake, then you reach a safe state, as we were discussing before. But for the cars, the outcome can be unsafe, because if you have a truck on your back at a short distance, then it would be unable to brake, and then it will cause an accident, which is exactly what happened in one case of Tesla suddenly braking in a tunnel, and then it was hit by a truck, and then there was a big accident with fire in the tunnel. You can imagine the consequences. So the output was safe and the outcome was not safe in that case. With digital twins, the big advantage is that you can evaluate the outcome. So you consider everything around you, the environment, and you can make this what-if analysis. So what happens if I brake, considering not only the system but the whole environment. So this is okay, easy to say but not easy to implement in practice, but this is what we want to achieve. So this was your first question. The other question was about okay, if it is attacked, the decision is okay. That is more generally a security problem. So as I said, with the intelligent systems, you have traditional cybersecurity problems, because if the system is not protected, so the attack surface has some holes, then it is of course vulnerable to cybersecurity threats, even the traditional ones. But in addition to that, you have adversarial attacks, you have data poisoning, you have many new classes of attacks, and you need to make a risk assessment, vulnerability assessment of penetration testing. I mean, all these techniques must be adapted to the nature of the system. So considering data poisoning, considering adversarial attacks. So this is part of the security analysis of your system.
Thank you, sir. Gracias.
Welcome.
Very good evening, good morning, sir. First of all, thank you so much for taking your time and showing us this presentation. It was very informative. And my question is again on the topic of autonomous vehicles. That I will give you two situations. First situation is this hybrid model that we are currently running. Some cars are autonomously driving, not fully autonomous, but they are driving autonomously. Some cars are fully controlled by humans. So for the AI systems, I don't think so. Human inputs are very predictable. And when someone needs to accelerate and deaccelerate, it cannot be predicted very accurately. Of course, the precision has some percentage, but it's not very accurate. So doesn't this current scenario can be manipulated to when all the cars can be automated? When every car has an AI system, then they can communicate with each other and then they will take actions on their behalves. So I don't think so that this current hybrid model is actually very, what is your thoughts on either we should continue with this model, the hybrid model, or we should wait and just transfer into an autonomous vehicles with all the cars being autonomously driving, or at least have some.
Mhm. Okay, this is also a very good point. It's about modeling the human behavior, I would say, the human factor aspect of semi-autonomous vehicles. So because if it's autonomous, then you don't have humans in the loop. But if it is a decision support system, and it is at the moment a decision support system for the cars that have this ADAS level 2 with automatic braking systems, lane keeping, and adaptive cruise control, which are the subsystems of level 2. It's you have humans, so you need to monitor the behavior, which is simple if you just need to monitor the fact that the driver has hands on the wheel. But if you need to go to these levels like level 3 or level 4, which is not yet full autonomy, but you need to monitor the behavior of the driver, also the level of attention of the driver. You need to make assumptions on how quick is the driver to take control of the car in case our autonomous system will not be able to control the car because maybe some sensors have failed. Well, this is very open problem, I would say. We don't have solutions for that. We are very skeptical about the fact that humans will be ready to take control of a car in a few seconds, maybe fractions of seconds. It depends on the situation. And this is subject to many criticisms by not only myself, but other big scientists and very famous American professors. They are criticizing this approach. Telling that it's not an approach that is safe and it cannot be demonstrated to be safe when you have this hybrid control in which you have humans together with machines. Because normally when you have a fully manual, then you can at least trust the level of attention of the driver, the level of training of the driver. But when the driver is not attentive because he or she is reading a book or texting and doing other things, but still for the regulation perspective, responsibility is on the driver. So he or she must be ready to take control of the vehicle. There is an ongoing discussion, but my perspective, which is shared by other scientists, is that this is not going to work. I mean, so as you said, either full autonomous or semi-autonomous as it is now, but these intermediate levels that make these strong assumptions on human behaviors, they are not going to work and make the system safe.
Thank you,
Thank you,
sir.
sir.
As we are running out of time, next questions can be taken up in the tea break.
Once again, thank you, sir. Your presence and invaluable insights on the topic, the role of modeling and digital twins for safer perception, inspired us and added great prestige to the gathering. Now, we invite Dr. Madhu Kumari ma'am, convener of rTIME 2025 and head of the department Electronics and Computer Engineering, to present a memento to Flammini sir as a token of gratitude.
Thank you, ma'am. Thank you, sir. Moving on, we are truly blessed to have Dr. D.K. Singh, sir, a distinguished academician and the Honorable Vice Chancellor of Jharkhand University of Technology, to deliver the final keynote of rTIME 2025. Professor D.K. Singh completed his B.Tech and PhD from Birla Institute of Technology, Sindri, one among the prestigious institutions of Indian subcontinent. He started his career in the academic field as assistant professor in the Department of Electronics and Communication Engineering at BIT Sindri. Later, he joined NIT Patna as a professor in Department of Electronics and Communication Engineering in the year 2012 and continued there till 2017. Being a powerful academic leader, he has served as the director of BIT Sindri and founding vice chancellor of Binod Bihari Mehto Koyalanchal University, Dhanbad, playing vital role in strengthening premier technical institutions. He is also a member of State Higher Education Council of Jharkhand and Senate of IIT ISM Dhanbad. Then he joined as a vice chancellor of Jharkhand University of Technology, Ranchi, in the year 2023. Professor D.K. Singh has been assigned with responsibility of Ranchi University, Ranchi, Jharkhand, this year 2025. His visionary leadership continues to elevate technical education and research in Jharkhand and beyond. Sir, please.
Sir, on behalf of the Department of Electronics and Computer Engineering and IMT Ranchi, we wholeheartedly welcome you to address the audience. Over to you, sir.
In 1947, and the semiconductor was also reported in 1947. 23rd, it was in the month of the December, right? I think it was December when this transistor was reported. How many of you are from the electronics? Please raise the hand. Electronics and computer engineering, right? Good. So the question is, before 1947, every century is dominated by a single technology. If you go through the 18th century, it's a great mechanical system, a steam engine, right? Then in 19th century, it was industrial, you can call mechanical system started taking place all around the world. But in the 20th century, in the mid 20th century, this a small tiny component, this semiconductor, right? It was not the semiconductor, rather it was started with the germanium, right? But the report of this transistor, junction transistor changed the entire world. So my dear students and the delegates, I am going to just throw the lights just to excite you the journey of this electronics and computing. Yeah, please go first. You see, before 1947, have you ever observed the radio system of your grandparents? If it's still there in your house, old house, it's a big radio system, right? You ask to your professor, you ask to your dad, there was a big, that was called radios, the vacuum tubes era. How many of you have observed the vacuum tubes? Any devices? Even the older one, the TV system, it was not the flat panel, right? Somehow you might have observed the tube was taking more space than your screen, right? So this was the era 1947. The era was the vacuum tubes, the electronics industry, the radio system. But 1947, this transistor was being reported, and so the bulb was used in the radios, TVs, early computers, bulky high power consumption. 1947, Barden, Brattain and Shockley, Bell Labs marked the beginning of the semiconductor electronics. And these three scientists, you might be observed, the Shockley was British scientist. He was highly egoist. You know, Britishers were dominating the world. So somehow out of these groups, there was a problem with compatibility. And when this was being reported, only these two, Barden and Brattain, reported about this. So in the January 1948, the Shockley again reported the junction transistor, right? So this was the journey, and all become industrialists. The problem with billionaire in India and billionaire with the rest of the world, this is a big difference. They become billionaire because of the invention of their products. And here in India, just I am joking, if you go through the list of the billionaire, they become billionaire because they got the land from the government, they got some fund from the loan from the banks, and a good policy from the government supports. But still we have a few billionaires on the basis of the innovation because of their R&D, right? But this India, 21st century India, now we are getting the billionaire list because of our R&D, startup and our innovation also. So next slides I am going, this point contact junction transistor, the rise of germanium based electronics. Then came the silicon. Texas Instrument produces the first commercial SI. I am just going to focus. This is the MOSFET, computer science. Which transistor is suitable to VLSI? It is MOSFET. Metal oxide semiconductor field effect transistor. This MOSFET is highly suitable to VLSI, very large scale integration transistor. Out of the transistor, we have two classes, the BJT and the FET. Out of the FET, this is the MOSFET, low power consuming devices. Then you go through, then came the era of the integrated circuit, the 1960s. Just 60 to 70, it is an era of integrated circuit, right? And MOSFET is the backbone of the integrated circuit. MOSFET is highly suitable to integrated circuit. So 60 to 70, the same time in the communication industry, right? The 70 starts your computing industry, the microprocessor, right? But I am here right now in 60 to 70. So 60 to 70, the communication industry, electronics communication industry, the carrier was taken by through the copper industries, through the copper. But the same time, the fiber was being introduced. So a lot of research were done to reduce the attenuation going through in the fiber. So about the 70, still now communication shifted from the copper to the fiber, and the same time you just come to 71, and here starts a new technology, new era of computation. Earlier your computer industry was dominated by the vacuum tube, large computer, mainframe computer. If you are loading a program, after 2 days or 3 days the results are coming. Still in our BIT Sindri, if somebody is your HOD is also graduate of that college, still we have 1959 we got a mainframe computer there. Still it is there. It was at par with the IITs that time. That institution is older than the oldest of the IITs. So here the 4-bit architecture was reported, then a start of the microcomputer revolution. Calculator, digital watches, color TV expansion, early personal computers. So VLSI revolution started taking place, rise of this microprocessor processing, then came your optical fiber communication, satellite electronics communication, CD player, digital. Now I am going to start focus here from the 90s. CMOS become the universal logic technology, the power efficiency plus scaling. Now the people started, the personal computing era started, how to miniaturize the circuits, and the VLSI era started, the personal computing started, and the same time the communication industry shifted from fiber, copper to the fiber. So there was a race between the computing and the communication speed. You know, there is a marriage between this electronics and computer industry, and that gave birth to the information technology. But you know, any marriage there is a compatibility problem. So same time there was a marriage of this communication and computing industry. So you requires a protocol, how to control it, how to communicate it faster, how to use the bandwidth properly. So that gave birth to a new technology, a new era of the research. The same time the fiber industries, people started reducing the attenuation in the fiber level, and it was from 0.2 dB per kilometer. A new group of researchers in the Bell laboratory, they started thinking, is it possible to reduce the attenuation further? Just I am exciting this young student about the research. So people reported now in the fiber, the traditional fiber, it is not possible to reduce the attenuation level further from 0.2 dB per kilometer. Then one group of the researcher in the Bell, they started thinking, no, we are going to work to a new kind of the fiber, optical fiber, where we can reduce the attenuation, and that gave birth to a technology, PCF, photonic crystal fiber, where air was being injected, right? A group of researchers from the Germany and the Italy also, the PCF now, they have a lot of research paper came through the Italy's and the other groups. So a PCF was being reported, right? So the 90s, you see the power of how to have a low power devices, right? Do you know the GPU? You also know the EPU? Graphe, how do you define GPU? Processor, what is EPU? Energy efficient processing unit, right? The same time in the CPU, in the parallel you have the EPU. The question is, every bit of the data takes a energy. So you're now billions of the devices, SoC, system on the chips, billions of the chips are there on the same, billions of the devices are same on the chips, right? So how to have a minimum power consumption, that is also one of our constraint, and that is also the research areas for the researcher, next level of the researcher to work on. So power efficiency means you require a chip that takes a less power, and same times you requires a scaling, means on the same chips now number of the devices, maybe integration should be higher, right? So you have to reduce it. How to increase the level of the devices. So rise of the laptop computers. So 90s, the dominance was the CMOS technology started dominating the computing technology. So embedded system, the microcontroller, automotive electronics, industrial automation, right, that started coming in this era, 90s to 90s. Internet and networking, so this was a merger of computation and communication, and the internet era came, and in this internet era, people on the same line, earlier it was dominated by the wires, now people started taking a data on the same line. Though the only thing is that the people are the bandwidth hungry. People now started demanding more data on the same line, right? So new technology was required to support a higher data speed on the same line, and that gave birth to 2G technology, 3G technology, 4G technology, 5G technology, and the 6G technology. So a generation of the communication protocols and the communication started shifting from, so on the same communication line, it can support all type of the services, because you on the chip, computing chip, you started having the camera, video, right, everything on the same chip. So this internet and networking era started dominating in our 21st century. So era 21st century started mobile era. Earlier I said that every century was dominated by a single technology. Now the 21st century, what is this technology? This AI technology, artificial intelligence technology, green technology, right? So backbone is your information technology. If I am saying information technology, means this is a merger of electronics and computer science, and I appreciate any IMT. The department name is electronics and computer science is the right name in the 21st century, right? So smartphones begins in 2007, iPhone, high performance system on the chips, Bluetooth and Wi-Fi integration. So shift to portable, connected, compact devices, rise of a smartphone, Wi-Fi, portable entertainment devices. So these are the industry which started dominating: Nokia, Motorola, BlackBerry, the launch of iPhone revolution. So a smartphone convergence, camera, music, internet in one device, start of application. So my dear students, especially I am focusing you, how to use your talent, because this is 21st century era has also given you enough opportunity to work in these areas. This convergence of the technology has given rise to many constraints, means any constraint in our industry is a research problem for you. Good research scientists are sitting here, they will be throwing you light. A constraint is always a research problem. Means you have a very good now problem, everybody is knowing the constraint. You might have observed the Elon Musk, somebody said that the rocket cannot be refueled, but he took it as a research problem for their industry. And when he asked this question to his teammates, do you believe that it can be refueled? So some of his junior colleagues said, sir, it is not written in the book. And what was his answer? He answered, God has not written this book. Somebody has written this book. That's why that constraint is there. I don't believe in any constraint. So constraint is a good R&D problem for me. And you have observed, I think 6 months back, that the rocket was recalled on the same position, it was returned and it was refueled, and that is going to give birth your space technology, that is a vehicle is now ready to take you to the Mars. It's a good revolution, right? So any constraint is a problem, a research problem for you. right? So application app era, at the beginning of the mobile, first design lifestyle. So Wi-Fi, this new standard, the computer science people, you know, this 802 point, all standards are coming to have a higher bandwidth, higher data rate, more coverage area, right? So Bluetooth standard for accessory, 3G network enabling video calling and the mobile data. Next, is the evolution of the laptop. Portable computing became the mainstream. MP3 player, portable gaming, digital camera, semiconductor advancement. Now come this advancement of the VLSI. Now the focus is on the chip was 130 nanometers, now have shifted to 45 nanometers, means this is the gate length. On the same gate length, whatever the device which you have integrated on 130 nanometers, now the same set of the devices can be integrated on the 45 nanometer of the gate length. So low power ARM processor, high density NAND flash memory was available, and because of this discovery, this invention, that gave birth to a new technology, new application, right, a new type of the industries. So miniaturization and the power efficiency. The industry shifted, electronics industry, how to miniaturize further. Now the industry is thinking about 3 nanometer to 2 nanometer, it is shifting, on the same shifting. And same time to have a low power consumption. Say smaller component, improved integration, growing use of system on the chips, birth of modern mobile hardware architecture was being reported in this decade 2000 to 2010. So impact, what is the impact on the society because of the miniaturization, shifting up to 45 nanometer, mobility become a default expectation, social media, mobile commerce growth, digital photography all become realizable here. So because of the miniaturization of the circuits, the computing speed started growing. The same time the communication industry started providing a higher data rate on the same lines, right? Successful transfer of the data from one end to the another ends. So set the stage 2010, the IoT, cloud, smart devices, mobile, first world transformed industry, user experience becomes a device driven. So nanotechnology and semiconductor scaling. So you see 135, how the electronics industry, still the miniaturization. The beauty of this electronics and computing industry. In other industry, when the new technology come, the cost is higher, but the beauty of this industry is that when the new technology come, the cost goes down. You are getting a good application, right, and good appliances at the lower cost, 65 nanometer to 45 nanometer, 32 nanometer. Are we getting this technology? Means the gate length, the billions of the devices we are integrating. Earlier it was on 65 nanometer, now 45 nanometer, now 32 nanometer on the same. So the same laptop on the same size, it will accommodate many applications, many devices will be there inside your laptops. That is the beauty of this technology, and still you cannot predict where it will go, and a line will be drawn, no further, right? So multi-core processor era came, advances enabling miniaturization, performance boost and energy efficiency. Moore's law and transistor doubling, you know, Moore's law was in the 60s, every 1.5 years it becomes doubles, right? So scaling from micrometer to nanometer. So what is the challenges? Challenges is how to dissipate the heats, right? Because billions and billions of devices you are integrating, heat is a big problem. The leakage, the quantum effects. So atom level material engineering, precise control of the doping structure, enable ultra thin You know the constraint of the nanotechnology. Suppose you are sitting here in the auditorium. Right now you are 100 people, and suppose 10,000 people have been allowed to sit here. What will happen? Now imagine a problem. So same problem when the number of atoms, number you are integrating more on the same chips, on the same size, there will be a lot of the problem, a lot of the issue will be there that you have to address. So these nanomaterials, the carbon nanotubes, graphenes, the new materials, 2D material, this is national, it was earlier called NIFT, now it is NIAMT, manufacturing technology. So your campus is famous for the material science, right? So this is also a manipulation of the materials. You have to explore materials suitable for this miniaturization. So silicon nanowires, quantum dots, deep ultraviolet, extreme ultraviolet at 13.5 nanometer, you see, shifted. High resolution patterning for nanoscale. Off कर दीजिए. So 3D transistor structure, better electrostatic control, reduced leakage and improved switching. Scaling limits, so quantum tunneling, power density, thermal issue, high manufacturing cost, these are the issues for researcher like you, engineers like you. 3D stacking, heterogeneous integration, neuromorphic and the quantum computing, smartphones and IoT, AI accelerator, high performance computing, medical devices, sensor, it started all being used here, right? So nanotechnology continues to drive the semiconductor evolution, leading to faster, smaller and smarter electronic system. Now 2010, this is billions of connected devices that gave birth to the edge computing, GPU and TPU, tensor processing unit, right, for the AI acceleration. Now advancement in the semiconductor nodes. Earlier I said that miniaturization start going 7 nanometer to 5 nanometer. Now it has come to the 3 nanometer chips. Really imagine on the same devices, number of, earlier it was 135, now 45, 65. Now it is possible to integrate all those billion devices on this 7 nanometer. Now it has shifted to 5 nanometer and 3 nanometer chips. These are the industries that are manufacturing all these chips. You might have gone through the NVIDIA. Have you gone through the success story of the NVIDIA? What is the turnover of the NVIDIA? 4 trillions. This GDP is more than the India GDP, right? A single industry. And you know the success story of that man? He belongs to a very humble background. You go through his life history, how he changed the GPU industries. UV, then is computer science students are there, you know the CISC-based and the RISC-based processor. This is the RISC-based processor, right? So electric vehicle, power electronics, now communication industry is shifting from the 5G to 6G. Still the 6G is not coming directly in the commercial market. We are all around the world, we are using the 5G, flexible and the printed electronics. So the future beyond Moore's law. What is now the electronics industry is working to come down to 3 nanometer gate length to 2 nanometers, right? So the quantum electronics, neuromorphic and the bio-inspired computing. This is the era of the AI. You want intelligent chips that will take the decision. So the biology, sense of biology you are integrating on the same chips, right? So bio-inspired computing era started. So friends, electronics industry from the vacuum tubes, to AI-driven quantum era devices, transforming every part of the human lives. Just I have touched within this time how the electronics industry has changed the world. I think we are lucky enough. If you ask this question to your faculty in 50s and the 60s, in the 80s, we have gone through all type of the technology, right? We have seen the radios technology. We have seen the there was a also an era where getting a scooter was very difficult in the 70s and 80s. There was a queue to get a scooter there. But this semiconductor industry, this electronics industry had changed the entire world so fast. I would like to quote here the Bill Gates. Bill Gates once said that still the mechanical industry, they have not put a lot of money in the R&D. If they have done a good research in the R&D, the automobile industry, the world should not have faced a problem of the energy. With 1 liter of the petrol, if the R&D was good, the vehicle can run to 500 kilometers. But you see the beauty of this mobile phone, now a common man can use it. How do you decide the quality of a citizen of the life? The per capita energy consumption and the technology. So this is the IT technology a common man can use. A common man can also buy a vehicle, a automobile, but he or she is not buying because of the petrol cost. So still a lot of R&D is required there in the mechanical industry to reduce the cost. You develop the engine, you develop a material so that it can run 500 kilometers with 1 liter of the petrol. Is it possible or not? You can develop a car, a stackable car, right? Suppose 6-seater car you are driving, nobody is sitting besides. Can it be stacked together, right? These are the problems which you can work there. So the beauty of this industry is there. So I am thankful to Department of Electronics and Computer Science and the HOD Professor Madhu Singh that a very good conference has been organized. So I hope a lot of research papers have touched the different aspect of this electronics and computing industry. You might have enjoyed it, and I appreciate the team of electronics and computer science. Let they should start a new conferences, new a specific domain on the EV, on the 6G, on the 5G, on the twin technology, what Professor was throwing the lights. So with these words, if you have any questions, you are free to ask. I have simply touched the basic part of this journey of electronics from 1947 to 2025, not the communication part, rather the electronics part. Yeah, the student. Otherwise, we will interact in the tea time. So thank you very much. Yeah, here's the question. Yeah, please.
Good evening, sir. Sir, I have a question that, as you remarked earlier, that the other industries are, as innovations are leading, the other industries' cost of manufacturing are increasing. But the semiconductor and nanotechnology industry, the innovation costs are decreasing. So is it because the recycling of semiconductor
Innovation
chips?
nahi, when the product cost, let us ask somebody, a CD player, a VCD player in 60s, it was in the lakhs. Only 2 or 3 person was having this. But you see, anyone can use these appliances. The cost is very low.
Sir, is it because recycling of the materials?
No, it
or
is not
any other
because
reason?
of recycling, miniaturization of the circuits. The same cameras, video camera, audio camera, right? All types of sensors you are miniaturizing on the same chips. This is millions, now billions of the devices on the same chips. Low cost. So technology, advancement in technology is bringing the cost down. but it is not same in the other industries. That is the beauty.
Thank you, sir.
Anybody else? So thank you very much.
Our heartfelt thanks, sir. Your participation and insightful views on the topic, development of electronics, have greatly inspired us and elevated the significance of today's gathering. Now, we invite Dr. Madhu Kumari ma'am to present our memento as a token of appreciation. Please, ma'am.
Thank you, sir. Thank you, ma'am. May I now request all the dignitaries and the faculty members to proceed to the NIMT canteen for high tea. Students may kindly be seated for a few announcements.